Welcome to Control System classes. The topic for today's discussion is Proportional Integral Controller from Electrical Engineering job. The proportional integral controller will produce an output actuating signal as a function of two terms. One is proportional to error signal, the other is proportional to integral of error signal. So we can write U of t is proportional to E of t plus integral of E of t into dt. To remove the proportional symbol, let us add constant called Kp, proportional in gain constant, and Ti is called integral time constant. So Kp into E of t plus Kp by Ti, integral of E of t into dt, where Kp by Ti can be called as Ki, integral gain constant. Let us take Laplace transform on both sides. So E of s will be equal to Kp into E of s plus Kp by Ti. Integration will become 1 by s. So 1 by s into E of s. Take the common term outside and rearrange the equations. We get U of s by E of s, which is nothing but the transfer function of proportional integral controller, is equal to Kp plus Ki by s. So this is the transfer function of proportional integral controller, and the transfer function is represented in the controller place, and this is my open loop function G of s. Again, this proportional integral controller major responsibility is to reduce the steady state error. The proportional integral control action, let us verify how it increases the order of the system. So the transfer function of proportional integral controller is Kp plus Ki by s, and the open loop transfer function G of s I have taken as a basic second order system. So it is omega n square divided by s into s plus 2 zeta omega n, where omega n is called natural frequency of oscillation, zeta is a symbol corresponding to the damping factor. So the feed forward function is nothing but the product of these two terms in cascade. So the feed forward function is omega n squared divided by s into s plus 2 zeta omega n into Kp plus Ki by s. Now this is my open loop function. Let us write C of s by R of s. It is a negative feedback system. So C of s by R of s is nothing but G of s divided by 1 plus G of s H of s. Let us examine. We have substituted G of s and H of s value is 1. G of s is nothing but feed forward function. Now let us examine equation 1 and 2. We have concluded that here the order is 2. Here the order is increased to 3. Here we don't have any zeros. Here a 0 was introduced at s is equal to minus Ki by Kp. So it means the proportional integral controller increases the order of the system, which may add more poles, which may lead to instability, but in the opposite side, it introduces a 0. We already discussed about the effects of zeros in first order system and second order system in the previous videos. So the zeros, when it is added, it will improve the transient response. It increases the speed of response, but with initial overshoot. That is the contribution of zeros, effects of zeros. So the transient response is improved, and also the proportional integral controller will make the steady state error to become 0. So we have 2 minutes to add the proportional integral controller. And also we had verified the steady state error. So this is feed forward function. To calculate the steady state error ESS, first let us solve E of s. E of s is R of s divided by 1 plus G of s into H of s. H of s value is 1. Substitute G of s with the feed forward function, and let us calculate ESS is limit s tends to 0, s into E of s in s domain, and we got the value of ESS as 0. So we had understood that the introduction of PI controller makes the steady state error to 0. It also increases the order of the system. It introduces a 0 to the systems. So let us summarize the concepts: open loop system, the closed loop system with PI controller. Initial order 2, now the order is 3. Initially we don't have zeros, now the 0 is located at minus Ki by Kp. So initially open loop system has 2 poles, now the pole is increased to 3. So this is the summary of PI controller. Reduces steady state error or makes the steady state error to become 0, increases order, introduces a 0. Let us verify the concepts with MATLAB program. like the top of our previous lecture about P controller. So CLC, clear all, close all, they are the basic commands to clear the command window, to clear the workspace, to close the previous opened figure window. I'm going to write the expressions in S domain itself. So I have used the command S is equal to TF of S. So this is my first initial function, plant function P. I have used a second order system 2 divided by S square plus S plus 2. To calculate the DC gain, I have used the command DC gain of P. What is DC gain? It makes S function to become 0. So the DC gain will be 1 for the given function. I am going to plot 4 plots in this picture. So I have used a subplot, 2 rows, 2 columns, comma first position. And the time samples also I had given here with a value from 0 to 20 with an increment of 0.01. The step input is given here. So step of P, comma, for the given time durations. So title is declared here. Then step info of P, we know that it will print the time domain parameters, rise time, peak time, settling time, transient overshoot, peak magnitude, peak time. Every parameters can be printed on the command window when we had used the command step info of the corresponding plant function notations. So this is without controller for second order system. Then I have introduced a PI controller. What is the syntax for PI controller? Feedback of controller into plant, comma 1. So controller into plant. Controller is KP is 10, KI is 5. So the function, the general transfer function is KP plus KI by S. So 10 plus 5 by S. Then the plant function is the given function. So it will be, the MATLAB will calculate the transfer function and it will also calculate the DC gain. And the step input is applied, the graph is plotted, and the step info is printed on the command window. And also the same is executed with the first order system of form 1 divided by S plus 1. So 4 plots are printed in the same figure window and 4 step infos were printed on the command window along with the DC gain. So let us see the results in the next table. So this is without controller, with controller for first order system. This is for second order system. This is the function with including the controller, and also when I substituted S is equal to 0, my DC gain is 1 for all. So I have normalized it in order to compare one plot with respect to the other plot. So this is the step info printed in the command window. I have taken the output and pasted in this tables. And I can able to conclude there my 0 introduction reduces my rise time. Initial rise time is 2.19. Now my rise time is 0.2 in case of first order. Similarly, for second order system, my rise time has decreased. My first order system will not provide more overshoot, but my second order system has increased overshoot because of the introductions of zeros. And also my peak time has reduced with adding PI controller. It means the added 0 with PI controller may adjusted my transient response, and hence the speed of response is fast. It also makes the steady state error to become 0. Here you can observe, here is my settling time is 7.74 without controller. My settling time has increased to 13.6. Why it has happened? I had given the consequences of PI controller. That my PI controller, when it is introduced, it may increases the number of poles, and hence it may make the instability to the system. It means my zeros had added more oscillations. So it takes more time to stamp the oscillations, and hence my settling time is increased in case of added zeros with the introduction of PI controller. So my rise time has decreased. So speed of response is improved. But with the case of second order system, as it becomes a third order system, more oscillations is prolonged during the transient response, and hence the settling time is decreased. What is settling time? The time taken for the system to settle within 2 to 4% error. Let us see the plot graph for the executed program. I have got the MATLAB output. So let us see here. So this is without any controller. So with controller, my steady state error becomes decreased, but I have prolonged oscillations because of the added zeros, but my speed of response has increased. So here it takes more time to reach the final value. Here initially with the less time itself it reaches a final value. This is without controller for first order system and with PI controller. Here also we can observe the changes in the transient response and the steady state error becomes zero with the introduction of PI controller. Let us realize the PI controller with inverting amplifier. So the first stage is my integrator, second stage is my sign changer. We know that here we need PI controller, not only I controller. If it is only I controller, we need an input resistance with a feedback capacitance. But it is a PI controller. In the feedback part, we have introduced a resistor. So the first stage will give the transfer function of, that is, the output E1 of t will be the integral of error signal E of t on the calculation simplifications. After simplifying the derivations we got, as it is an inverting integrator, minus R2 by R1 into 1 plus 1 by S into R2 into C2. So this is my first gain. My second gain is a sign changer, as we have same value of resistor. So it will provide my gain as minus 1. Let us find the overall gain as U of t by E of t, multiply both the values, and my gain is R2 by R1 into 1 plus 1 by S into R2 C2, where R2 by R1 is Kp, R2 into C2 is my integral time constant. So by adjusting R1, R2, C2, I can able to control Kp and Ki, which may affect the pole location and hence the stability of the system. So overall, we can able to conclude that the PI controller introduces a zero, increases the order, it improves the transient response, that is, it increases speed of response. So thank you.